On this worksheet, we're just going to practice a few different types of nomenclature problems, kind of a variety of nomenclature that we've learned all year long. Starting right off the bat is an ether molecule, and these are tricky because ether is not its own functional group in terms of IUPAC, so when we're naming an ether molecule, we either have to use a common name, which involves just naming the two alkyl groups and then saying ether, like in this case, cyclopentyl isopropyl ether, or we can name one portion of the ether as a substituent on the other half of the molecule, which is a little bit trickier. So this, if we wanted to do that, we would consider this to be the parent chain. We would name this as the substituent on the parent chain. This as a substituent, its name as a substituent is based off of the name of its corresponding alcohol. That is 2-propanol. So this would be 2-propoxy as a substituent. So we would call this 1,2-propoxy cyclopentane. Why the 1 and the 2 and all of that confusing numbering? The 1 is referring to the location of the substituent on the cyclopentane group. The 2 is referring to the location of the oxygen or the OH group on that 3-carbon chain. We could also call it isopropoxy. Isopropoxy, that sounds so funny. Isopropoxy cyclopentane. The common name of this alcohol is isopropanol. So as a substituent, that would be isopropoxy. Well, that was a tough one to start with, so let's take a look at this one over here. Hopefully it's easier. This is an alkane. With alkanes, we're looking for the longest continuous chain of carbon atoms. I'm just going to number those. So let's say 1, 2, 3, 4, 5. Looks like we just have a lot of a tie here. 6, 7. For our branches, we've got a methyl, we've got another methyl, and then this, which is an isopropyl group, or it's also a methyl ethyl. We would also call this 1-methyl ethyl. I like the isopropyl better. We're going to alphabetize these substituents. So the isopropyl comes first alphabetically, 5. I just realized that I'm numbering this backwards. We need to number it to give all of our substituents the smallest possible set of numbers. 1, 2, 3, 4, 5, 6, 7. So this is a 3-isopropyl, 2,6-dimethyl heptane. And let's take a look at our next one underneath down here. Looks like our longest carbon chain is going to be right here. We want a number to give our substituents the lowest overall set of numbers. So if we go this way, then our substituents are going to be a 2, 4, 4. And if we number in the other direction, we're going to get a 3, 3, 5. If it's kind of hard to tell just initially by looking at it, what you can do is add those numbers up. And the lowest sum is going to be the best set of numbers. So that means we want to go back to the original numbers, 1, 2, 3, 4, 5, 6 from left to right. Alphabetize these substituents. We have an iodo on carbon number 2, so this is 2-iodo. And then we have our 2 methyls on carbon number 4 and 4. 4,4-dimethyl hexane. Now we have a cyclic. So here is our carbon chain. We want a number to give our substituents the smallest possible numbers, which is going to look like this. So we have 1, 1, 2. But we want these in alphabetical order, so we'll start the name with 2-ethyl, follow that up with 1,1-dimethyl cyclopropane. Very long name for a very little molecule. Down here, we have another cyclic. When we have cyclic molecules, we get to choose which carbon is carbon number 1. And typically, because we're looking for the smallest overall set of numbers, if we have 2 branches on the same carbon, that one is probably the one that we want to make number 1. So if I go like this, I have a 1, 1, 2, 4. That looks pretty good. Put those in alphabetical order. Bromine comes first in the alphabet, so it's going to be 2-bromo. And then after that is going to be our ethyl group, which is on number 4, 2-bromo, 4-ethyl, 1,1-dimethyl, cyclohexane. Now we have an alkene. Our longest carbon chain is right here. Looks like whether we number it left to right or right to left, the molecule is symmetrical. We're going to come up with the same thing. We've got our methyls on carbons 3 and 4. 3,4-dimethyl, 3-hexene, or we could say 3,4-dimethyl-hex-3-ene. And then don't forget that we need to include the stereochemistry in this molecule. This is trans, so we could say trans here. Or we could classify it using E and Z. This is an E, because Z refers to Z, Zame, Zide, which is the same as cis. Now down here we have an aldehyde. For aldehydes, we always want to make the aldehyde carbon number 1. This is a 3-carbon chain, no substituents. So this is a prop 2-ene. If it didn't have the aldehyde, it would be prop 2-ene or 2-propene. With the aldehyde on it, we just drop that last E and add Al. Remember that we don't say the location of the aldehyde because it has to be on carbon number 1. By definition, that's what it means to be an aldehyde, to have the carbonyl group on carbon number 1. So this is prop 2-ene Al, or you could call it 2-propene Al. And over here we have a ketone. The ketone group is taking priority, so that one has to be carbon number 1. No matter what, like that has to be carbon number 1. So we want the rest of our branches to have the smallest possible number, which I think means we want to go this way, 1, 2, 4. If we went the other way, it would be 1, 3, 5. Yeah, so we definitely want to go this way. We want to name our chloros first, 2,4-dichloro, cyclopentanone, and we don't have to say that it's on carbon number 1 because everybody knows that it's on carbon number 1. That's the rule. Here's another one. This is a ketone, and our prioritization here is to give the ketone the smallest possible number. So that means we are definitely going to number it from right to left, even if that's not the best set of numbers. That's what we have to do. Name our substituents. On carbon number 3, we have a chloro. On carbon number 5, we have a methyl. And then this is actually I'm going to put the number in front, 2-heptanone. Or you could say 3-chloro-5-methyl-heptan-2-one, which is what I almost said. Here we have another alkene. Let's just start right away with the stereochemistry. Our ethyl groups are on the same side, so this is either cis, or we could call it Z. So we'll call this guy Z. We want to number this. No matter how we number this, left to right or right to left, our double bond is going to be on carbon number 3 going to carbon number 4. So when there's a tie like that, we want to number it to give whichever substituent comes first in the molecule's name. That one should get the smaller number. And since the bromine is going to come before the methyl, we want that one to have the smaller number. This is 3-bromo, 4-methyl, 3-hexene. We've got 2 left. We've got a benzene derivative. When we're naming benzene derivatives, it's good for us to look to see if we can find one of those, like about 9 or 10-ish benzene derivative molecules that gets its own name. This molecule right here, if we're ignoring this part, this is phenol. And so we want to name this molecule as phenol. We don't want to name it as a benzene with an OH and a nitro and stuff like that. So we're going to name this as phenol. And we're going to name this phenol with a nitro group on it. So this is going to be nitrophenol, all one word. And then we want to indicate the location of that nitro group. So this is going to be carbon number 1 because it's a phenol. So this, we could say that it is 2-nitrophenol. Another option that we would have is to say orthonitrophenol. When the two substituents are side by side on the ring, then we can use the ortho notation. Last but not least, we have an alkyne with alkynes. That takes priority in the numbering, so we want to number this molecule from right to left, 1, 2, 3, 4, 5, 6, to give the alkyne the smallest possible number. Our branch is on carbon number 5, so that's 5-methyl. And then our double bond is on carbon number 2, so that is 2-hexyne.